Hey guys, last set of notes for gas laws today. This is the last little bit, and it's just sort of a variation on the ideal gas law. So really, you've learned everything you need for the test. We're going to review for the test and be ready just like we do in school. We're starting back at the beginning, working the whole way through and getting you guys good and ready. So the last thing we're going to do is sort of adjust the ideal gas law to include density. If you think back to the Penny's lab, density is mass over volume. We've got volume in the ideal gas law. Sure, V is already in there. If you think of number of moles, if I tell you I have 5 moles of carbon, you could figure out its mass, its total mass. You go to your periodic table, and it tells you that the mass of carbon is 12. 5 times 12 is 60, and there's your mass. So you're able, given the periodic table, to be able to figure out density of a gas. When we go through some fancy math and sub all of that into the ideal gas law, this comes out. MP equals dRT. You know what most of this stuff is. P is pressure, T is temperature. We're good with that. R we've been using, and I would suggest, and I'm going to remind you then, you're not using stuff on the test like notes and whatnot, but I would recommend writing down R. 0.08206 liter atmosphere per mole Kelvin. Not worth memorizing. Worth using whenever we're doing the ideal gas law, yes. Worth memorizing? No. I memorize it because I wrote it so many times. I've been doing this for a long, long time. So, some new things in this equation. M is molar mass. We've been calling that the periodic table mass to remind you guys where to look for it, and it's in grams per mole. M is going to be in grams per mole. The mass of 1 mole in grams. Great. For density, capital D, when we did this with the pennies, we did grams per milliliter. Milliliter's pretty little, because there was a lot of mass in that solid. Solids are dense, especially metals. So for density here, now we're on to density of a gas, which is going to be a lot lower. Gases are your lowest density state of matter, so instead of grams per milliliter, we're going bigger. We're going to say since they take up so much space, density's in grams per liter. There you go. Now, to remember this equation, you could look up the derivation and go through substituting and all, or you could learn this one. I had a girl the first year I taught this, I believe, raise her hand and say, I know how to remember it. These are not my words, these are hers. She goes, Mount Pleasant equals dirt. I'm like, what? MP equals DRT. I do see dirt when I look at DRT. Those are her words, not mine. This is not an insult. I live in Mount Pleasant. So, we're good on that. So, not my words, but there it is. So to use this problem, and I'll show you actually another way to remember it that I think is even more disturbing. Here we go, using the density equation. Let's put these values in. I'll do this one in the blue. Density of a gas was found to be, there we go, density equals 2.0 grams per liter at, pressure. 1.50 atm. Good so far. And 27 Celsius. I don't like Celsius. 27 plus 273. We got to stay in that Kelvin habit. 300 Kelvin. And R, yeah, it's already there. I want to know what is the molar mass M of the gas. So if I do this, if I divide both sides by pressure, my new equation is M equals dRT over P. And I have an even more disturbing way to remember that to solve for molar mass. I was looking this up for AP Chem, and it said, it had a teacher say, to pretend that molecular mass was a kitty. I already do cations are positive, and she said kitty, and there was a little ear and tail drawn on the M, and I was like, this person is weirder than I am. But she said if that's a kitty, to remember that all good cats put dirt on their pee, like they bury in the litter box. I was like, oh no, but there it is. Again, not my words, but you might remember it. I look at it and I cringe when I think of that now. So what I'm going to do is substitute in for this. I think you should still be able to see. Actually, what I'm going to do is just erase where I've written that equation and fill in those values, DRT and P, because we have it up at the top. So my density is 2.0 grams per liter, R 0.08206, liter atmosphere, mole Kelvin, and my temp, 300 Kelvin. So there's my top. The bottom of the equation would just be my pressure, 1.50 atmospheres. To cancel if I want, there's liters and atmospheres and Kelvin, and it leaves me a molar mass. And so that you can see on the screen, I'm going to write it up here. Leaves me an answer in grams per mole. When I enter this in my calculator, 2 times 0.08206 times 300 equals, divided by 1.5 equals, I got 33. Now, if I wanted you to, you'd be able to go back to a list of substances, find one with a molar mass of 33, and make a good guess at what this compound is. Now, I don't know if it's one element or if it's a bunch together in a compound, but if I said, what do you think this is? Anything with a molar mass of 33 could be a right answer. Because this would be, like if you went to the periodic table, or if you did a formula mass calculation where you add up masses, that's what that is. It's really the mass of the compound that's a gas in this situation. So that's pretty cool. You have a practice problem. It's not too bad. And there's some more examples there on YouTube. They're not me. They're somebody else. How fast do gases move? Really, really fast, right? Yeah. That's sort of the whole point. We've been talking about that from the kinetic molecular theory, which we'll review later. Our review of that is coming up. Gas particles are in constant rapid random motion. Spinning the bingo ball, watching the bingo balls bounce around in the old school bingo machine. True. That's how gases move. But here's today's message. Lighter gases move faster than heavier ones. You're like, okay. Lighter stuff bounces around better than heavier ones. If I were to fill a machine like that with ping pong balls and spin it, they would bounce more than golf balls. Really close to the same size, but lighter versus heavier. Gas particles are the same way. We talked about diffusion, mixing through movement of random molecules bouncing all over the place. We talked about effusion, and yes, I giggled, and some of you might also, escape of gas under pressure through a small hole. The rates, how fast gases diffuse and effuse, change with their molar mass. Lighter moves quicker. Lighter will diffuse faster, lighter will effuse faster. So if I want you to compare rates of effusion, say, of two gases, you go to your periodic table. Today's lesson is, yes, we need the periodic table for this. You go to your periodic table, find the mass, write the mass, compare the mass. So if I'm looking at hydrogen, H2 with a mass of 2, and I'm looking at neon with a mass of 20, hydrogen is going to effuse faster than neon because it's lighter. This guy, Thomas Graham, forever ago, English scientist, came up with this idea. I think he's English. He might not be, but he's old. He came up with this idea that he could calculate how much quicker one gas would effuse than from another. So if I ask you to compare hydrogen and oxygen, what I'm looking for you to do is go to the periodic table and say H2. Hydrogen is 1 times 2 is 2. Oxygen is 16 times 2 because it's diatomic 2, so 32. Hydrogen 2, oxygen 32, hydrogen faster. Lighter, faster, done. Graham came up with this equation where you put the rate of one over the rate of the other. Then on the other side, you take their masses, you flip the masses, and you take the square roots. So my simple answer is hydrogen is faster than oxygen. You can use Graham's law, and I set it up in your packet. You can use Graham's law to see how much faster. And when I put in the numbers, I get that oxygen is 4 times slower, or you could say hydrogen is 4 times faster than oxygen. But that makes sense The takeaway message is just hydrogen is smaller, so it'll move faster, including diffusing faster and effusing faster. So that's a review of your definitions and a look at gas speeds. And addition, MP equals DRT. That's the last content for the chapter. So I'll see you next time and get ready to review.